In this video, we're going to discuss half-life. I'm going to use simple illustration to explain half-life. I'm going to derive decay equations and also solve examples. So let's begin with building understanding what half-life is. So consider this as a radioactive sample. In this sample, we have 20 atoms. 1, 2, 3, 4, 5. 1, 2, 3, 4. So we have a total of 20 atoms in this sample. So I'm going to write N naught, that is initial number of atoms. I'll say 20 atoms. They are 20, okay? As time goes on, they start decaying in a random way. One can decay here, one can decay here. So radioactivity is a spontaneous and also a random process. But for the purpose of teaching, I'm going to take this decay to be occurring serially just to explain what I mean. So that time, let's say the half-life of this sample is 2 years, for instance, okay? It means that after 2 years, 10 of these atoms will decay, which is half of the original number. The original number is 20. So after 2 years, half of it will decay. So this will decay, 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 giving us how many now? 1, 2, 3, 4, 5, 6, 7, 8. So this will decay and this will decay. So 10 is gone, leaving us with 10. That's the meaning of half-life. The time it will take for half of the atom present to decay and leaving you with half. That is half-life. So for this sample, we assume that half-life is 2 years. So after 2 years, 10 will decay, leaving you with 10. Now, after another 2 years, that is when your time counts 4 years. This 10 that is left will decay again. We have another decay where 5 will decay, leaving you with 5. So this 5, this will decay, this will go, and this will go. That's after 4 years. So that is what half-life is all about. So it is the time taken for the half of the atoms present in a sample to decay. Okay, so we're in good position to solve this problem. Now, this problem says if the fraction of the atoms of a radioactive material left after 120 years is 1/64, what is the half-life of the material? And these are the options that are given to us. So, to solve this question, we'll give it this approach. When the time is 0, before time start counting, we have complete number of atoms there, okay? It has not started decaying, it's still whole when the time is 0, all right? After the first half-life, that's when time gets to the first half-life, this will decay into 2, leaving you with half of it. Half of it will remain. After the next half-life, that is 2 half-life, this half will decay again to quarter. That is half of this half, which is now quarter, as after the second half-life. Then after the third half-life, this quarter will decay to its half, that is 1/8. So at 3 half-life, we have 1/8. Let's continue this side. So at t equals 4 half-life, okay, we're going to have 1/16, which is half of 1/8, right? Then at t equals 5 half-life, we're going to have 1/32. That is half of 1/16. Remember, we are given 1/64. So at t equals 6 half-life, we're going to have half of 1/32, and that is 1/64. So for us to have 1/64 fraction left, it means this sample has undergone through 6 stages of its half-life, and the time corresponded to 120 years. So we're going to say 120 years corresponds to 6t half-life. And that suggests that t half-life is 120 upon 6. And t half-life will be 120 upon 6. 6 in 6, 1. 6 in 12 is 2. So T half-life will be equal to 20 years. So the half-life of the sample is 20 years, and that is option B.